Hey everybody, how's it going? We're going to go ahead and talk about solving for um, our resistance total, our current total, our voltage total, even though it's supplied, as well as the voltage drops as it goes around our series circuit. Okay. Before we get started, let's go ahead. Let's do a quick little review that for Ohm's law, we have voltage, right, is equal to I times R, or our current multiplied by our resistance. All right, knowing that if we were to then cover up R, if we want to find our resistance, we can take voltage divided by our current. And if we want to solve for our current, all right, we can say our current is equal to our voltage divided by our resistance. All right. Um, Remember, these are in volts, amps, and ohms, right? If you want to convert to milliamps, that is fine. Just make sure that you are converting back to amps when we solve for Ohm's law. Okay? All right. First off the bat, let's go ahead. Let's find our resistance total. Okay? For our resistance total within a series circuit, remember resistance total is equal to the sum of all your resistors or all your components. So in this case, I have my resistance total is equal to R1 plus R2 plus R3, right? From there, I can plug in R1 is 470, R2 is going to equal to 1.2 k ohms, that's 1200 ohms, by the way, and then R3 is going to be 270 ohms, all right? So we have 470 ohms plus 1200 ohms for R2, okay, plus 270 ohms for R3. From there, we just add them up, and then RT is going to equal our total resistance, 1,940 ohms. All right. Now, you can convert that to kilo ohms if you really want to. We're just going to leave it as is for the time being. All right. Okay. Now, next up is our total current. All right. For our total current, what we're going to need to do, so remember, if we were to use Ohm's law, we need our total voltage and we need our total resistance. Okay, so we're going to say that our current, all right, total current is going to equal to our voltage total divided by our resistance total. Okay, now if we take a look up here, notice they supply us with our voltage total. It's going to be 9 volts. So we're going to say we have 9 volts divided by our resistance total, which is just calculated for right there. So it's divided by 1,940 ohms. All right. So then that tells us that our resistance or our current total, right, is going to be 0.00463, right, amps. Okay. Now we're going to need this number later when we calculate for the voltage drop at each one of our components. Okay. But just for the time being, let's go ahead. Let's convert this to milliamps. Okay. Reminder that milliamps is equal to 10 to the negative third. All right. So we need to move our decimal place over 3 times. So then we get 4.63-ish milliamps, right? And that's going to be our total current. Okay. A nice little reminder, a nice little simple thing that's good to know about our series circuit is that our IT is 4.63 milliamps, all right? But so is the current, right, at each one of our components, okay? So our current at resistor 1 is the same as our total, our current at resistor 2 is the same as our total, as well as the current at resistor 3 is the same as our total. So that's going to be good to know later on when we calculate for our voltage drops, okay? Now, as for voltage, let's go ahead, let's just put it out there. Our voltage total, we already said, is 9 volts, okay? But what we need to do is we need to solve, right, for the voltage drop at each one, okay, at each one of our components, okay? So, according to Kirchhoff's voltage law, right, he stated that our voltage total is going to equal to our voltage drop out of component 1 plus the voltage at 2 plus the voltage at, right, 3, okay? Now, in order to solve for these, each one, what we're going to do is we're essentially going to complete Ohm's law, right, 3 different times for each of these components. And then we'll break them up, and then the result that we get, so that voltage at each one should add up to, right, our 9 volts. Okay, so let's go ahead, let's break it down. Let's do our voltage at resistor 1. Okay, we're going to say that the voltage at resistor 1 here, right, is going to equal to our current, right, at resistor 1 multiplied by the resistance of resistor 1. Okay, so in this case, our current at resistor 1, remember our current at resistor 1 is equal to that of our total current. So we're going to say this is going to be 0.00463 amps. Remember, we have to use amps. We're doing Ohm's law. Okay, multiplied by 470 ohms, which then tells us that our voltage at resistor 1 is going to equal to 2.18 volts. Okay, and that's how we do it for the first one. Okay, now all we need to do is repeat the process for our other 2 resistors. All right, so voltage at resistor 2 is going to equal to our current at resistor 2 multiplied by the value of resistor 2. Okay, so our current is the same. So we have 0.00463 amps multiplied by the amount of ohms in resistor 2. This one is 1.2 k ohms, so we're calling that 1200 ohms. So now doing that, we get VR2 is equal to our current multiplied by our resistance. So we get roughly 5.57 volts. Okay. Last but not least, let's go ahead. Let's find it for resistor 3. Okay. Yet again for resistor 3. Move up here a little bit. Our current at resistor 3 multiplied by the value of resistor 3, so the amount of ohms. Okay, reuse that current again, 0.00463 amps multiplied by 270 ohms. All right, so we need 270 ohms here. Okay, which then gives us a total value of resistor voltage at resistor 3 should be 1.25 volts when we multiply those together. Okay, so now we got our voltage at each one. Okay, now let's go ahead. Let's check for Kirchhoff's theory, right, which states that our voltage total should equal out to our voltage drop at 1 plus a voltage at 2 plus a voltage at 3, right? So in other words, we have 9 volts is equal to 2.18 volts plus 5.57 volts plus 1.25 volts, which when we go ahead and we do the math, right, we should get 9 volts is equal to right around 8.9-ish volts, which if you ask me, I would say, right, that works out, that checks out. So I would say that works for us. Stay tuned for parallel.